Good afternoon, everyone. We are conducting a workshop on next generation automatic modeling and simulation with AMS software, and today is the third day. Yeah. So today's session will be on TD-CD/FT response properties for crystals using band software, and this session will be taken by Mr. Srijit from Nyro Research India. So I would like to just recap regarding the slides and the recorded sessions where I've uploaded once again. I'll be sharing the screen. Yeah, hope you can see the Google Drive. So this was the first day of the session where I had uploaded the YouTube recorded session link as well as the resources that was taken by Dr. Ole. And there are even tutorials as well as the slides available. And the second day session, that was yesterday, I have uploaded the YouTube recorded session as well as the slides and the tutorials of the software, which was taken by Dr. Franco last day. So I've shared this Google Drive link to everyone, all the registrants. Hope you have received my email. And I'm sorry for an inconvenience. Actually, there is a technical issue for the speakers to join. So meanwhile, I'll just walk you through some of the overview of the applications on the basic of building structure using AMS and band engine.
The hands-on tutorial is indeed about periodic systems. So I wanted to basically begin with some overview about crystalline structures and how to handle them in the Amsterdam modeling suite. So first and foremost, we indeed start up the GUI. And so one of the big advantages of the Amsterdam modeling suite is that there is a basically seamless handling between molecular and periodic structures of all dimensionalities. So one can treat molecules just the same way as nanowires, as monolayer 2D materials, or then as 3D periodic structures. Of course, for doing so, this depends on the program you are using. So indeed, it needs a program which is able to handle periodic systems. That is not ADF, but it is, for example, BAND, which is our 3D or periodic DFT program. This is a real space code, meaning that it indeed can handle all different kinds of periodicities on equal footing, which is, for example, not possible in plane wave code. As an example, we have Amsterdam modeling suite also comes with the plane wave code, namely Quantum Espresso. There's also an interface for WASP, so these two are generally a little bit more efficient. However, they are not able to treat a proper 2 or 1D periodic system. So having said that, first and foremost, how do we treat periodic systems in the graphical user interface? As soon as I switch to code like BAND, there is another option field emerging here, which indeed lets me set the periodicity. So there can be none, there can be chain, slab, and bulk. And then I can, for example, load in some crystals or construct them. There is some template library for various different common crystalline structures. I can pick one, and there will some window will open, and it's already pre-filled with some default values. And I can then just load this back in. So this is then the minimal part of the unit cell I'm seeing here. One can then click on this button here. which enables one then to, which basically shows then the periodic images around the actual unit cell one is dealing as model with. And so yeah, in this way one can basically then say start and manipulate the system, shift atoms around and do various things. There is then under, commonly under edit, there's a separate field regarding crystals. It includes again this aforementioned structure library. There's a constructor from the symmetry space group. And then there are various different tools. So for example, to generate slab models, to generate supercells, to map atoms into different conventions for unit cells, and all things like that. So yeah, apart from that, of course, one can, you can build your own model, of course, from scratch. So for that, let's say you can, for example, set the different lattice vectors, either in terms of vector lengths and angles between them, or explicitly as vectors, as shown here. And so I see there is a question. Sorry. Okay. And yeah, so that's a way basically to construct a periodic system from scratch. Another way, of course, and this will be the most common one, is you get some starting structure from, say, a database or from external source, from a previous calculation. And so yeah, within the Amsterdam modeling suite, let me delete this example here. You can basically import coordinates, meaning structure files, just via this file and import coordinate options. Alternatively, there are also ways to indeed download it from some crystallography database or websites, and our graphical user interface also supports the import of ZIF files. And yeah, indeed, that's what we're going to start with. So let me introduce you to the first example. This is a palladium disulfide crystal. So I wasn't able to find this system in any database, so I assume it doesn't really exist. However, the 2D slab model or the layered material exists, and that's also what we're going to deal with. Before we do that, let me just show you how to generate a 2D periodic model from a crystalline model. So you can find this file as part of the download package, and then you just go under file, import coordinates, and then just pick the palladium disulfide ZIF file. So this is this, and again, we take a look at the actual crystalline structure. And as you can see, this is a layered material, say similar to graphite. And so as we will just see in this tutorial, this material has some interesting properties. So basically, we now have loaded in the crystal structure, and the first thing we can, for example, we don't have to, is to map those atoms back into the first unit cell. So I assume here they already were, in case one ends up with a system like this, where this is completely placed outside. I can just reiterate this feature, and it will basically push the atoms back into the original unit cell. So the next task is then to isolate these individual layers. So what we're going to deal with is we have two different systems, and we're going to look at their band structures. The first one is a monolayer or bilayer material. The second one is the monolayer. And so in order to do this, we can again use our, so first let's focus on the original unit cell. And then we can enable here the generator for slab models. that allows it to specify the Miller indices of the cutting plane. And this cutting plane can be then offset by selecting an atom, as I have done here. So it shows a plane, but as far as I can see, that's an incorrect one. So please ignore that one. And then I can click on Generate Slab. Note that I have set here, pull that up again. I can only slice 3D periodic systems, so let me repeat that. So as you can see here, it also there's also an option to set a specific numbers of layer. So meaning to say how often is the original unit cell before it is turned into a 2D periodic system, how often is it repeated in the axis or along this vector specified by the Miller indices. So we're going to do this again. We pick this single atom here, and we're going to generate a bilayer material. Maybe I should also increase this so that this becomes more visible. Sorry for that. So yeah, for now we can then basically just save this file as a B-layer, give it a name, Palladium S2 as B-layer, and save that. So yeah, it will complain. We will set the options later. For now, I just want to show you the generation of the models. Before we come to that, I'd like to ask, are there any questions? We agreed before, so whenever you have something which is not working or some open questions, just raise your hands in the chat tool, and either Ole or me directly will try to entertain your questions.
I think it's okay.
Still fine? Okay. So yeah, now we have basically stored this file. And the second thing we're gonna do is we just, we can basically just revert what we previously have done. Note we didn't save this input file now, so we are back at our 3-dimensional structure, and we just repeat the same procedure for the generation of the monolayer. So we basically pick our atom, these Miller indices are fine, and we set number of layers equal to 1 in order to generate the monolayer. So now, as you can see, this turned into a 2D periodic system. This looks like something one might just for convenience map the atoms back to the original unit cell, which I just did. And again, so we then save this file and save as, and we name it monolayer. Again, it complements, we will address that later. So basically what we have done now is we essentially stored 2 structures, and so there was a question, how to dope particular atom or delete a particular atom in the periodic slab. I can show you this. So there's essentially no difference to a molecular model. What you can do is you select the atom, say you want to change the element type, and then you right click once it is selected, and then you pick the option change atom type. Then there will be a periodic table popping up, and you can give it, say in our case, you can turn that into a palladium atom. There will be a warning here because this is all already an existing structure, so it doesn't adjust for any bond length or so, which is fine in our case. And it will also explain that. So, and then, yeah, that's basically a doping or changing of atoms. Alternatively, you can also just pick one of these editing tools, and then let's say this allows you then to place an atom somewhere in the unit cell. You can then say adjust its position by say pressing Control 1, 2, and 3 to get different perspectives, look at it in X, Y, and Z direction, and that's let's say if you pick this, and then you can drag it with while holding the right mouse button down. That allows you to shift this atom in your viewing plane, and then if you basically repeat that for the different viewing planes, you can basically manipulate your system that way. Alternatively, what you can do, so the question was also about deleting. Deleting is pretty much the same. So you can, let me see, is there an option here?
Yeah.
I'm not seeing it. Yeah, so here there is delete atoms, or even easier, once this is marked, you just hit the delete key and it will also disappear. Just to revert those steps. So alternatively, what you can also do is eventually, in some cases, change the bond length. However, I think it doesn't let one do this now because
It's
this is already a fully connected structure indeed. Hoping that this answers your question. Let me come back at our original model. Mistyped the file name I just saw, but that's actually not a big deal. So next, what we're gonna do now that we saved the structure, indeed, I'm gonna walk you through the settings which are needed to perform a reasonable calculation for band structures while still retaining some efficiency. Obviously, these periodic DFT calculations, they can be quite expensive, especially if dealing with the real space code. However, using 2D periodic systems only and a slightly minimalistic description and set of options, you should be able to tune the calculation time down to a reasonable level for the sake of this hands-on session. So what we're going to start with is obviously this structure is already sort of optimized. So for the present moment, we do not need to re-optimize anything. So what we're going to do is there is another calculation. Yes, I will come to that. How to calculate the density of states, I will show you in a second. So we pick a single point as option here. There are alternative ways, as Feda was already talking about in the morning. You can do geometry optimizations, transition states, and basically all the options which are possible for molecular systems can usually be done for periodic systems as well. This is especially the case since we converted almost everything in our software stack to the AMS environment, and that basically gives them easier access to that. So we move on. Obviously, the periodicity stays as a slab, so 2D periodic system. And next we have to select our density functional description. So for the present purpose, I just picked the PBE functional because it's reasonably universal and still delivers a reasonably good description. And we saw already the warning a couple of times. Indeed, this system includes heavy atoms, especially the palladium atom. And for that, a scalar relativistic description is at least advisable. As we are going to look at the band structure and thus also at unoccupied orbitals or crystal orbitals, we are using a slightly bigger basis set. In that case, I limited that to the DZP, the basis sets, as we were mentioning before. These are again Slater type like orbitals, so technically they are handled numerically in bands. However, they are designed to always resemble the orbitals used in ADF. Those are Slater type functions. Accordingly, the basis set notation here is the same. And yeah, we're gonna pick the double zeta p basis set. So then we use a large frozen core, which basically assumes the role of a pseudopotential in a certain sense. However, this is really consists of actual orbitals whose coefficients are not changing during the SCF iteration. And for now, we're gonna select the numerical quality normal. I will come to that, what that exactly is in a moment. So then we have two options here. We select both of them. The first one is to calculate the density of states. That should answer Phoebe's question. So this is basically as easy as that. You just have to tick this box here. It will perform the calculation of the DOS after the SCF iteration is concluded. And yeah, we also tick the selection of the band structure. So then we basically go to further options for the band structure. And what we're doing here is then we show you this on the next slide. So this should, so basically for periodic structure calculations, one needs a K-space and sampling of the Brillouin zone. And for performing the band structure calculations, this sampling is even increased along the paths on which this sampling is performed. So we select here 0.03 reciprocal bores, and then we, for the sake of performance, we limit the energy range in which we are evaluating the bands. That ranges from 20 electron volts above the Fermi level down to 15 electron volts below. So with this, we're then basically ready. I just saved this example again. So file and save, and then we can go and file and run, which will make the ADF jobs window pop up, and it directly starts the calculation. As you can see here, we can monitor what's going on by clicking on the log file here. And while the calculation is running, we can already prepare our second example here. For doing that, let me come back to this Palladium monolayer. And what I'm going to do is I want obviously to keep the same settings. So what I'm going to do is just import coordinates, and I import the, let me first delete my atoms here, and then I do file import coordinates, and I load back in the monolayer model. And then obviously we have to pay attention to give it the right name. We will store it again on the Palladium disulfide bilayer, and we confirm that we want to replace this file. So then basically we retain, that's a quick way to swap out your structure and still retain the same options. We store this file by file save, and we basically queue it in for running. So after the first job is concluded, the second one will start immediately, and we can then afterwards take a look at the results. So we are going to wait for this calculation. We open the log file. So as you can see here, it will indeed perform an SCF calculation, which is converging rather rapidly. As you can see here, this error converges down quite nicely to the 10 to the minus 6, which corresponds to the convergency threshold. And then afterwards, so it also lists the K points. So the K points, as said, are the sampling points in the reciprocal lattice of the crystalline material. And this is what we basically selected to evaluate the band structure. So as you can see here, this involves a much larger number of individual K points. However, they turn out to be evaluated rather quickly. We should almost be done with this example here. So yeah, there's a little bit of waiting time involved. While we are waiting for this, let me also come back. So this job has finished now. Let me just explain very quickly. I was mentioning this before. There's this option in the main tab here, numerical quality. And the settings we put here is basically, so this normal setting, this is just an umbrella term for a lot of different numerical parameters. What is relevant for our case, for example, would be the K-space here. So again, this is also hidden behind some predefined values. However, it's always possible to set your own one. And you can set here different integration grids, so regular, symmetric. You can also set manually the number of K points in each direction, to be used for this periodic electronic structure calculation. So we take a look back at our second example that is already in and running. This will run slightly slower than our first example because basically the number of atoms is doubled in this bilayer model. But while we're at that, we can already take a look at our preliminary result, at our first result. And for doing that, we basically just in the ADF Jobs Manager here, we select the first example here, and then we click on the SCM logo here, and we select band structure. So this will open another graphical user interface tool, and it will load in the band structure calculated for this monolayer system. So slightly enlarge this. What are we seeing here? This is slightly zoomed out, but if you zoom in here on the very left side, what are you seeing is the Brillouin zone, so the reciprocal lattice. And so I have a 2D periodic systems. That's why this is an area instead of a volume. And what these symbols show here is basically the sampling paths which is used to generate or project the band structure onto. This you can see also here. So this can be changed interactively. So this is then used to generate the band structure. Alternatively, there are also things possible here that one can switch to the actual real space view. So you can see the actual atoms. And then say you can do things like selecting one and then say pick bands or the density of states of those individual atoms here. And so what you should see now is the F atoms of that palladium atom. Of course, you don't see very much in that case. Let's say if we look at the DDoS of the palladium, then that's still a total one. So I should be able to indeed. No, this is the way high. So this shows me the palladium contribution of the palladium D bands in that case. And similar DOS analysis can be done for the rest of the atoms and for all different shells then, of course, as well. So there's that. Let me clear up this view again. Yeah, just turn back to the cumulative DOS. The bands. I can then also, yeah, so there's another feature in here. As you may have noticed, indeed, the band structure here has different colors, and that is a result of that we basically implicitly we calculated also the so-called fat bands, which are which take into account the contributions from individual orbitals. And so what are we seeing here? There are different colors. And so whenever, say, in that case, some band turns red, that means that indicates that this band has a dominant S character in these relevant parts of the Bernoulli zone. So and then blue corresponds to p orbitals and green to d orbitals. So then let's actually look at our system. By the way, one can zoom in this band structure picture. One can zoom, I think, horizontally. Yeah, so you just put your mouse underneath on the horizontal axis, and with the mouse wheel you can then zoom in and out. Accordingly, also can also zoom in and out. So, and as you can see here, in this case, yeah, looking at the band structure, you will find that yeah, Fermi level. Indeed, Fermi level is this gray line here. Thank you very much. And you can see that yeah, there is indeed a slight band gap. You can hover over here, so it will give you an exact number of the horizontal and vertical coordinates. So the second number is the energy value of that band at that location in the reciprocal space. So we have a occupied band below the Fermi level, which is around at an energy of 5.56 electron volts, negative electron volt, and the lowest unoccupied band and crystal orbital has a energy of minus 5.3. So there is a difference of roughly, what is that, 0.26 electron volts. So not very much. That basically makes it a semiconductor, and yeah, so this is basically comments. I'm not sure what you mean. Yes, it depends on what you take as reference, the Fermi level to be at 0 electron volts. I think that is a matter of definition. So in the way it is calculated here, it is calculated, if I'm not mistaken, with respect to some isolated atoms and their solution, and so the energies you get out of that are basically what you see here. However, it's true you can reset that, and for some applications this might be more handy. However, in the definition or how band works on the technical level, you will see this Fermi energy at some usually negative energy value. But yeah, that is indeed whether you think of your energies as with respect to the Fermi level, then it is of course at 0. Or you pick some other reference, as is the case here, and then you will get a different value. The second question here is band calculation with hybrid functionals. They are done in a very similar way, as you just select a different functional, and but otherwise, no, the K points are always the same. So the K points is always something where you evaluate some crystal orbitals in a certain with a certain K vector, basically. That's how it works. So there, this is at least in the case of bands. the band gap option selection.
So maybe you can show in the log file, there should also be a shortened model.
On the band gap in the log file, yeah, so there is a band gap here in the log file, but I think the question was about something slightly different. So the could you please repeat the band gap option selection? So I assume you mean the selection to calculate the band structure. The band structure can be calculated by ticking this box here, so in the main settings panel. And what I did then is I clicked on this arrow here, so this always means further option on the very right of this calculate band structure option. What I then did was just increase or refine the interval values. That's basically the interval after which the bands are evaluated along this sampling path, which is then laid out here. I hope that answers your question. Otherwise, let me know what exactly you mean. Okay. Good. Then let's take a look back at our second calculation. Again, we have a certain number of K points to evaluate afterwards in order to obtain a density of states and to sample that properly. So I guess we have to wait for a tiny little bit more, but we should be almost at the end. So yeah, I can monitor, of course, your progress, but as you see, this is indeed the last step, and we are done. So again, we repeat, we come back to the ADF Jobs Manager. We now select the B-layer job and repeat the same thing. We open the corresponding band structure module for this system as well, by clicking on the SCM symbol and selecting band structure. So again, we get yeah, pretty much the same thing, our reciprocal unit cell, our real space system here, and our fat bands, or colored band structure, plus the density of states projections on the right side. And let me slightly enlarge that first. So again, comparing the two now, what we are seeing here is that there is indeed a tiny little difference caused from when going from a mono to a B layer. Indeed, we see now that there is some slight little bit of informally occupied or fully occupied band now reaching over the or across the Fermi level, and there is some sort of band, unoccupied band, which almost reaches down to the Fermi level now. So this allows one to deduce that this B-layer system should be more conducting. Indeed, if we come back at the log file here, we also can see that there's essentially no real band gap here. At least it is significantly smaller than what we had here before. I'm not sure how this is exactly evaluated, but the fact that we see something different here is probably because we used a finer grid to evaluate our band structure here. So you can see this is actually a good example where the sampling of the K-space does indeed matter. So probably if we would have picked more K-space, more K-points here, we would also see that this number goes down to 0. So indeed, this means now that this system is essentially, at least to some extent, conducting, while the monolayer is more like a semiconductor. Indeed, and this example was taken from a previous study. I included the citation here. where indeed these researchers argued that this material would allow one to realize a basically a logical junction on electronic elements out of a single material just by having a two electrical contacts made out of a bilayer or multilayer, and then the electrical junction is indeed then a component consisting of a palladium disulfide monolayer. So this concludes my first example. If there are any questions, I hope you were able to follow the calculation. Depending on the machine you're running this on, this may take, of course, slightly bit longer. However,